This is lesson 3.5, and we're going to be moving on to a new kind of function, this one called a rational function. We have just spent the last several lessons talking about quadratic functions and polynomial functions, and now we're going to look at these kind that are called rational. A rational function or rational functions are quotients of polynomial functions. This means that a rational function can be expressed as f of x is equal to p of x divided by q of x, where both p and q are polynomial functions. Q of x is not 0. That is always stated because we cannot divide by 0. The domain of a rational function is a set of all real numbers except x values that make the denominator 0. So they give us the first example, and it says, suppose you had this, and we looked at q of x, and it happens to be given to us in factored form, then the domain would exclude 0, would exclude 2, and would exclude -5. When we talked about rational expressions earlier, we called these, let me write it neater, exclusions, and that is still important. All right, we're going to skip this arrow notation for right now and try to get to the first few questions. Here we go. Let's take a look at number 1. It asks you to find the domain. All you need to do to find the domain is look at the denominator. You're looking for exclusions. This should be very familiar. You take x minus 15, set it equal to 0, solve, x is positive 15, and that is the exclusion. We would usually write it in a more negative sense and say x cannot equal 15. So we will choose A, and it says it is the set of all x's such that x cannot equal, and we will simply type in 15. Number 2, it wants to know the domain of the rational function. So again, I'm going to look at the exclusions, which means I'm going to take the denominator, x minus 7 times x plus 3, set it equal to 0 because those are the values I must exclude. Using the 0 factor property, I know x minus 7 is 0, or x plus 3 is 0. That means x equals 7, x equals -3 are both exclusions. So I will type in 7 and -3. They already have it in the set notation. Number 3, same type of question. Find the domain of this. So I will look for the exclusions. This time, when I have the denominator, which is x squared minus 121, equal to 0, I have to do the factoring. Well, this is the difference of squares, so I will factor it into x plus 11 times x minus 11. Using the 0 factor property and skipping a few steps, we can see that x is -11 or x is positive 11, and those are the exclusions. X cannot be -11, x cannot be positive 11. My math lab wants these exclusions separated by commas. The fourth one, I'm still asked to find the domain, so I'm looking for the exclusions. I have x squared plus 8 equals 0. That's the denominator. Set it equal to 0. This not only is not factorable in the real numbers, it's not factorable in the rational numbers or the real numbers. Do you remember that the sum of a square plus something cannot be factored? Let's suppose that you left the idea of factoring and you said, well, I'm going to try the square root property. X squared is equal to -8, which means x is equal to plus or minus the square roots of -8. -8 simplifies, the square root of -8 simplifies the square root of -4 times the square root of 2, or 2i square root of 2. X is equal to plus or minus 2i square root of 2. These cannot be domain exclusions, and you don't have to go this far because these are not real. There are not any real numbers that must be excluded. So there are no exclusions. When you have an x squared plus a constant, you're going to have no domain exclusions. That means, it doesn't say it here, but that means that the domain is from -infinity to +infinity with no breaks, no exclusions. All right, let me shrink this down a little, because domain exclusions result in either. There are two kinds or two ways that the domain exclusions manifest themselves on the graph. One way is the exclusion that disappears when the function is reduced. It's an exclusion, but it gets reduced out of the expression. We get what are called holes. There are holes in the graph. The other is you get what is called, and this might be a new word to you, vertical asymptotes. These occur when the exclusions remain after factoring. So let's focus first on the vertical asymptotes, and let's define them. A vertical asymptote is indeed a vertical line. All of these dotted drawings are drawings of vertical asymptotes. The line x equals a, meaning x equals a constant number, is a vertical asymptote of the graph of f of x if f of x increases or decreases without bound as x approaches a. Now let me explain that in everyday English. You have a vertical asymptote if, let's suppose that this is the line x equals a. Maybe x equals 2 or x equals 5. As the x's of the function get closer to a, the graph is never going to cross a. It is going to either shoot up toward +infinity, or here's an example over here. As it gets closer to a, the graph is going to shoot down toward -infinity. So that's what they're talking about. F of x, which is the y value, increases or decreases without bound. In other words, as you get close to this thing that we're calling a vertical asymptote, your graph is either going to shoot up, snuggle up against the line but not touch it, or it's going to shoot down, snuggle up against the line but not touch it. All right, I think I have a missing question. I'm going to fix that off camera. All right, there are a few more note panels here that are helpful, and I'll come back to them as I need to. All right, so we've defined what a vertical asymptote is. It is a vertical line that a rational function, or some other types of functions possibly, but in this lesson, vertical asymptotes are vertical lines where a rational function, as it gets close to that x value, either shoots up or shoots down. All right, locating vertical asymptotes. If f of x is p of x over q of x, it's a rational function in which p of x and q of x have no common factors. Now that's important. That means it is reduced. And a is a zero of q of x. In other words, a is a solution of the denominator. Then x equals a is a vertical asymptote. Vertical asymptotes occur at the exclusions denoted by q of x, but only if it was in reduced form. Now, there's a little note, this comes out of your book, and it says, a value where the denominator of a rational function is a zero does not necessarily result in a vertical asymptote. There is a hole corresponding to x equals a and not a vertical asymptote in the graph under the following conditions. The function's equation in which a does not cause, wait a minute. Oh, I missed part of a sentence. The value a causes the denominator to be zero, but there is a reduced form of the function's equation in which a does not cause the denominator to be zero. So this example shows it much better. What if this is your rational function? You look at this, and immediately, if I ask you about the domain, you would say x cannot be 2 because that's an exclusion. But if we reduce this by factoring the numerator and factoring the denominator, then it is equal to this. Nevertheless, and by the way, this is a line. This is f of x, y, equals x plus 2. But the domain exclusion remains. That means the graph of this will be the line y equals x plus 2, y-intercept at 2, up 1 over 1, but there will have to be a hole or a gap at x equals 2 because it was a domain exclusion. We will talk more about this later. And by the way, the hole is very difficult to identify if you're using a grapher. All right, let's go on to some of these questions. Number 5, find the vertical asymptotes, if any, and the values of x corresponding to holes, if any, of the graph of the rational function. All right, so what we want to do first is find the exclusions. Well, I have x plus 3, which is the denominator. I set it to 0, and I know that x equals negative 3 is an exclusion. Now, is it a vertical asymptote or is it a hole? All you have to check is, can this be reduced? Can it be simplified? And if it can be simplified, does this x plus 3 go away? The answer is no. It's already in lowest terms. So this is a vertical asymptote at x equals negative 3. It is a vertical line, so do not write it as just negative 3, but instead write it as the equation of a line, x equals negative 3. And there are no holes. All right. Number 6. We have a function here. The numerator, x plus 3, the denominator's in factored form, it doesn't reduce. The minute you see that it doesn't reduce, you know there are no holes. So now, what are the vertical asymptotes? Well, take the denominator, x times x minus 1, set it equal to 0, you will get an exclusion at x equals 0, you will get an exclusion at x equals 1. Those are vertical asymptotes. The only time you have holes is if something reduces out of the function. So x equals 0, comma, x equals 1. There are no holes. Number 7. I'm going to rewrite it down here. H of x is equal to x over x times x minus 3. Now, if I started just at the very beginning and said, are there any exclusions? You would say yes, x equals 0 is an exclusion, x equals 3 is an exclusion. But remember, it might be a hole, it might be a vertical asymptote. Looking at it closer down here, I see that this divides out and this is equal to 1 over x minus 3. Because the x factor divided out, that makes it a hole. X equals 3 is a vertical asymptote, so this one has both. So